Swayam Prabha. Digital India. Educated India.
Welcome you all to the next class on Inorganic Chemistry of Life Principles and Perspectives. During the past 3 classes or so, I have been trying to revise what all I have taught, which I put under the title called highlights. And towards the end of the previous class, I was talking to you about the nickel enzymes. Anyway, I will bring back the highlights of the nickel enzymes once again now here, and then try to complete the rest of the enzymes associated with it under the highlights category in this particular class, and then quickly start the tutorial parts from the next class onwards. Okay, you see that in case of the nickel enzymes, nickel is involved in variety of reactions such as hydrolysis like urea hydrolyzing to give ammonia kind of thing, hydrogenases where the 2H plus 2 electron giving to H2, and it is a kind of a reversible kind of reaction depending upon the nature of the enzyme, whether it is in the oxidized form or the reduced form. Also carbon monoxide dehydrogenase going from CO to CO2, and things such as the methyl coenzyme M reductase, nickel superoxide dismutase I have told you earlier too. I will just show some highlights. Glyoxylase, of course, I will not be discussing about this. Cis trans isomerase I will not be discussing because we have not done even in the main lectures, and acetyl coenzyme synthase, the methyl part of the coenzyme becoming the transfer into this methyl coenzyme CoA. So, these are some of the things, and we have looked at in the regular course urease, hydrogenase, dehydrogenase, and the methyl coenzyme reductase and glyoxylase, not glyoxylase, I think probably superoxide dismutase, etc. Okay, coming to the kind of a nickel centers that you find, this is the dinickel center which is present in the urease enzyme, which is bound to histidines and aspartic, etc., bridged by a carboxylic group, etc. Then you have a coenzyme factor F430, nickel iron hydrogenase, iron hydrogenase, and then you have the carbon monoxide dehydrogenase, carbon nickel carbon centers, and this is in SOD kind of thing. Okay, coming to the highlights of the hydrogenase, as you have seen there are 2 parts of the steps. One is called the activation step, other is called the catalysis step. In the activation step, in presence of the hydrogen gas, it gets activated because of this SH gets protonated and one of the hydride is bridged. And this is the active species. This active species further undergoes reduction and see it gets oxidized to nickel 3 plus, and by removing losing 1 electron and the proton, and then you have a hydride transfer going over there, and then you have a hydrogen again oxidative addition, then losing another proton. So, you have totally 2 protons coming out and 2 electrons coming out in the reaction, here 1 and then 1 more here, 1 hydrogen plus 1 H plus, leaving the pre step activation step. So, therefore, you can see the H2 giving 2 H plus 2 electrons is completely over there. This is the kind of a center which explains the catalysis of this. Okay. So, during the process you have a redox also occurring for the nickel center 3 and 2, 3 plus to 2 plus. So, this is the kind of thing. In case of nickel superoxide dismutase, just like the way that I talked to you about the manganese case, in the first stage the 2 plus ion goes to 3 plus, as you can see here by the removal of H2O2, and the next step again it will go back to 2 plus with removal of O2. So, first step is the nickel gets oxidized and O2 minus dot gets reduced. In the second step, nickel 3 plus gets reduced and O2 minus gets oxidized to O2. So, you can see that nickel 2 plus, it represents 1 mole of the superoxide, and then this will bind here by replacing the water or other coordination, and this undergoes redox to nickel 3 plus, and it represents the proton, it will throw away the hydrogen peroxide, and then you have your 1 more mole of the superoxide. 1 more of the mole of the superoxide again can bind over here, gets activated by the base from the protein, and this in presence of the proton will push the O2 out, and then you have the cycle being done in the SOD. So, main things that you need to remember is the first step nickel 2 plus go to nickel 3 plus and then becomes H2O2. In the second step, the nickel 3 plus goes back to nickel 2 plus and then gives out the 1 O2. Okay. Now, looking at another enzyme which is carbon monoxide dehydrogenase. Carbon monoxide dehydrogenase is a very involved kind of an enzyme or complicated enzyme, as you can see, enzyme with the A centers, B centers, C centers and D centers, and you can see several of the B and several of the C and then A centers, etc. here. So, all of these are involved in some activity or the other, particularly the electron transfer. Finally, the reaction takes place over there. The electrons are generated and the protons also, then these are translated through this or transported through this C2, then B1 and then D and then B2 prime or C2, C1 prime, etc., etc., etc. Here at this cluster, the reaction of the CO2 to CO, which is a reverse in the reaction, and otherwise you have the CO2 to CO2. As you can see over here, that is the cubial like cluster, but it is not cubial because this particular part is broken. So, you have one nickel, other is the iron. So, the nickel center is connected to the protein through the cysteine moiety, and the iron center is also connected through both cysteine and histidine moieties over there. This, in presence of the CO binds at the nickel center. The CO binds at the nickel center, and this in presence of the OH, and this OH will act as a kind of a nucleophile at the CO here. As you see that. So, that means this proton is out. This proton, how will it be out? There will be some protein based base which will pull out this particular proton. So, it will make, and you see the intermediate here, the intermediate is the kind of a carboxylate which is bridge kind of a thing through carbon and the oxygen kind of thing. So, this in presence of the water will give you CO2 out, and the protein is more or less obtained, but in a different oxidation state. So, again so this needs to be this is the reduced kind of thing, and therefore, it will go back to the oxidized form of that, and this is done by the external proteins here over internally. B oxidized will go to B reduced, okay, and the reduced of this will go to the oxidized, and this is triggered by the ferredoxin. So, ferredoxin oxidized to ferredoxin reduced, then B reduced by B oxidized, and this will in turn will convert this particular thing back to this particular thing. So, this part is the kind of a the carbon monoxide binding, the carbon monoxide ejecting, and here the redox state is coming back. So, ping and the ping pong kind of a mechanism that one can see that. So, in fact, this whole electron transfer path was identified by xenon, filling the xenon with that. These are some of the highlights of the nickel. Now, look at the copper enzymes. The copper enzymes, it's called type 1, type 2, type 3. Type 1 and type 2 both have got 1 copper. So, type 1 has nothing to do with the copper 1, or type 2 has nothing to do with the copper 2, and this is completely involved in the electron transfer, and this electron transfer is also, this gives the blue color to the protein, and because of the kind of a charge transfer that you have from thiolate to the cysteine, that is what is involved. Then you have type 3 with the 2 copper centers which will act like a bridge for activation of the oxygen, therefore it will be found in the oxidases. Then you have a type 4 kind of thing, then copper A, copper B, these are found in the cytochrome oxidase. Then copper Z, which is not so well known, which is a I think the 4 tetranuclear cluster, and then you have copper zinc, which is in the superoxide dismutase. Okay. So, tetranuclear copper Z center, copper Z, is found in nitrous oxide reductase, which I have not explained to you. The 4 copper atoms are coordinated by 7 histidine residues and the bridged by the sulfur atom in these ones. So, as I said, these kind of things are blue copper proteins, type 1 copper protein. You can see in all of them the commonality is that the one of the bond is very long and distorted geometry, just distorted from the regular geometries. Why is it distorted regular geometry? Is because copper 2 will go to copper 1 when the electron transfer, and copper 1 goes back to copper 2 during the electron transfer. So, therefore, means the protein should be able to accommodate both the copper 1 and copper 2 simultaneously during the electron transfer. Therefore, the nature has chosen a very asymmetric kind of a geometry in such kind of a blue copper proteins, and that is one way moon in disguise. And even these proteins will exhibit potential as low as 200 to as high as 700 millivolts because of the primary coordination differences, not so much so, but secondary coordination differences which are most important in this. So, type 2, one of the type 2 activities is galactose oxidase. Galactose, the primary alcohol of the galactose, that is C6 alcohol of the galactose, is converted to the aldehyde. The protein, there is an unusual aspect, that is this particular thing. This is a tyrosine, this is a cysteine. Tyrosine and cysteine are joined together after the translational events, that is after the protein is synthesized. This is called post translational event, and this acts like a cofactor here. Okay. And this protein center, the copper center, is activated when you have an electron is lost, therefore, you have a radical is formed. This radical is the one which is involved in that. Now, this is very well poised for the alcohol to bind here, and alcohol binding you can see, and then followed by redox. So, once you have the redox, that this gets oxidized, because this O dot radical versus it will generate a radical at the carbon center, this carbon center, and you can see here, and therefore, you have a RCHO is coming out, therefore, the reduction oxidation of the substrate, reduction in the copper center. So, copper has gone to copper 1. Now, to bring back the copper 2, then this needs to use the oxygen. See, in this oxidase, oxygen is not used for binding to the substrate, oxygen is used for to bring back the protein to the normal state. This is copper 1. So, then in presence of the oxygen, O2, then you have again O2 binds here, one electron transfer, that will be pick up the proton OOH, and this will replace by the water and then goes back to the normal. So, this is an oxidase. Unlike that happens in case of the iron centers or iron enzymes, O2 is not involved in the beginning, O2 is involved only when the enzyme is reduced at that stage to get back to the normal. Also, I have talked to you in case of type 3 is involved converting tyrosine through various oxidative processes to finally to melanin kind of thing. The huge number of reactions, as you can see over there, is possible. And of course, one can take this as the kind of an enzyme tyrosinase which can add hydroxyl moieties. So, let us see in the tyrosinase enzyme you have a 2 copper centers. These 2 copper centers are copper 1 state, and both are connected by 3 histidines, but no bridging ligand at all. So, this kind of a center in presence of the oxygen, here you can see the oxygen gets activated to O2 2 minus, because there are 2 copper centers, each one can go from 1 to 2, 1 to 2, 2 electrons, then 1 to 2. And this is now good enough for converting the substrate. So, substrate for example, if you have catechol, so catechol can bind here and then you get the oxidized product of the catechol out. The enzyme is still not in the normal state. This can do one more catechol be converted into this. So, it binds and then catechol and then back. So, it can do two consecutive steps of the catechol reaction to get back to the normal. On the other hand, if you have a mono OH, that is like phenol. So, at this stage if you have, instead of the catechol you have the phenol will bind to one of the coppers, one of the copper centers, and the other copper center will hydroxylate to the second the neighbor and then in the second step this gets oxidized quinone. So, either you get from catechol to catechol one more catechol to catechol or phenol to catechol. So, this is the kind of a, so these are the things which are involved in the melanin formation also. There are some cases where the copper centers where you have type 1, type 2, type 3 all together in one. This example is ascorbate oxidase. Type 1 is shown as T1, type 2 is shown as T2, type 3 is shown as T3. Type 3 has got 2 copper centers. So, in this case it is not 0, it is O oxidized, 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 oxidized. So, all the 4 coppers are in copper 2 and the first electron will enter into the type 1 and the second electron will enter into the type 2 and these 2 electrons are added to the type 3 and one more electron will activate the species into the O2 kind of a O2 minus that will add and that will be thrown out because already the electron is added to that and at the cost of the water. Now, you have a T1, T2, T3 with 1 O minus because out of the O2 1 O is trapped here, 1 O is gone out as a water and this particular O is a kind of a species which is bound between the T1, T2 and T3 centers and then one more electron will reduce the T1 and then that will be the totally the 4 electron and that will become the water and then goes back into this. So, you have a type 1, type 2, type 3 all together also and this is superoxide dismutase here instead of this is also bimetallic, but it's one is zinc, other is copper, not both are zincs, not both are coppers also. So, first O2 minus will attack at the copper center and this will undergo redox, then it will break and this will give the O2. In the second case O2 again binds over here and it will kick out the H2O2. So, it is exactly reverse to what you find for the manganese. The manganese first step will give H2O2, second step will give O2. In the copper zinc superoxide dismutase, first one is O2 and the second one will be the H2O2. So, the similar kind of thing. Now, let us come to the enzymes of zinc enzymes. Zinc is again non-redox metal ion, but shows all kinds of reactions. Hydrolases which will make the hydrolysis, peptidases which will break the peptide bonds, oxidoreductases which will bring oxidation reduction of the substrate. You can also add oxygen and remove the oxygen. Transferases groups are being transferred, lyases where it is the bond is broken without the water and the ligase the bonds are added when they from a thing. So, you can see there are so many different kinds of the coordination course, single zinc center or multiple zinc centers, all of these are there. Take one example which is a carbonic anhydrase enzyme. In the zinc center you have water gets activated and this is more like a hydroxyl. Now, there is a water present here, this water is attached to the site protein chain and this particular water is replaced by CO2. So, and that CO2 is held close proximity to the hydroxyl moiety. Therefore, this hydroxyl moiety will the oxygen of the hydroxyl moiety will show will give a nucleophilic attack at the carbon center, not at the oxygen center, and that will give an intermediate called carbonate kind of thing, metal ZnOCO Zn kind of a metal cycle, and this will break in presence of the water and comes out with all this, as you can see. This is the way the enzyme purifies the CO2 from the blood thing. Similarly, even peptides of various kinds. I have talked to you carboxy peptidases of C-terminal, carboxy peptidases of N-terminal. This is one of the examples for C-terminal, the peptide binding here, having a nucleophilic attack of the hydroxyl group, forming an intermediate, and then this will break with the protonation and gives the carboxylic part and the amine part of that, and then you have water will be replacing. So, it is very similar kind of a mechanism. So, many other things are there. Okay. So, now let us come to the other enzyme, which is molybdenum. Molybdenum is, in the case of the molybdenum, we can look at the oxidoreductase properties much more. That is why I have not highlighted in case of the zinc, but they are present in both the cases too. Okay, molybdenum is very well known enzyme is molybdenum nitrogenase. Molybdenum nitrogenase, which converts the nitrogen into ammonia. Then you have a host of enzymes called oxidoreductases. It could be nitrite reductase, pyridoxal oxidase, DMSO reductase, biotin sulfoxide reductase, xanthine oxidase, dehydrogenase, aldehyde oxidase. There are a variety of oxidoreductases. This is one kind of an enzyme, these are all one different kind of an enzyme. In all these cases, the molybdenum goes through dioxomolybdenum, which is molybdenum 6, to monooxomolybdenum, which is molybdenum 4. In this process, the oxygen is given to the substrate, and the reverse process or oxygen is taken from the substrate. So, when it is molybdenum 6 with the dioxo, it will add the oxygen to the substrate. When it is a molybdenum 4 with monooxo, then it will take away the oxygen from the substrate. And that, if you remember, that is the basic mantra of the molybdenum enzymes. Okay, we talked about the nitrogen fixation or nitrogenase or nitrogen conversion to ammonia, which has got a cofactor of this kind. And you see, this is all one iron sulfur cluster, another iron sulfur cluster, which is bridged by these sulfides, and one unidentified kind of a ligand, which is close to that of the either the halide or the sulfide kind of thing. It is at this center of the molybdenum where actually the reaction or the conversion of the nitrogen to ammonia takes place, and I will be showing in a while that highlights too. Now, when you come into the cofactors of oxidoreductases, you see that this moiety is called a pterin moiety, and this is a phosphate, this is a sugar, this is a base. So, it is basically a kind of a nucleotide with the pterin molecule. So, another molecule, so di, or you can have also mono kind of thing is another kind of a mono. So, all these kinds of cofactors are present in the molybdenum enzymes. Let us look at the nitrogenase functioning. It is a very complicated protein. You have an iron protein, and this is a molybdenum iron protein. And then the iron protein has got the iron sulfur cluster, then you have a P cluster here, and then you have many other cluster, which is the FeMoCO, that is called iron molybdenum cofactor. So, this is where actual catalysis occurs. All these are involved in the process of electron transfer, and the ATP, magnesium ADP is involved in the energy process, because that is what the one which couples the electron transfer into between the iron protein with the iron molybdenum protein, which couples, it is the magnesium ATP hydrolysis will activate the enzyme, and that will connect the electron transfer, as you can see, going from here to the 4 iron 4 sulfur cluster, from there to the P cluster, and the P cluster to iron molybdenum cofactor, and where the electrons are added to the okay, the oxidoreductases, here I have shown the example of xanthine oxidase mechanism. This is the xanthine oxidase mechanism, where you have only one single dithiol containing pterin moiety, which is bound as here OOS, and xanthine, and xanthine basically binds over here, because of the oxygen can give an attack on this particular center and bind, and in the process the molybdenum 6 will go to molybdenum 4, and the kinds of changes will come to 5 and back to 6. So, 6 to 4, 4 to 5 and 6, this is done outside the cycle of this one, and this is done in the cycle. So, there are a lot of changes happen, xanthine, hypoxanthine to xanthine, xanthine to uric acid, all of these are done by oxidoreductases of the molybdenum, as you can see that over here. Okay, there are some other things, let us look at very quickly. Some nitrate to nitrate. Nitrate is NO3, nitrate is NO2. So, you have the enzyme center with the S cysteine in presence of the nitrate. Nitrate binds to this particular center. If water is there, it will be replaced, and then you can see the nitrate thing, and that will undergo redox from 4 to the 6 and pull out the oxygen from the nitrate. So, here the enzyme is in the reduced state, takes the oxygen from the substrate. Here the nitrate is substrate, nitrite is the product. So, therefore, it becomes nitrite. Now, the enzyme has gone to the molybdenum 6, then this has to come back to 4, and that is done by the external redox enzymes by giving the 2 1 electrons and then bring back to the, take away the 2 1 electron, 2 times 1 electron and give this one. So, 6 to 4. So, you have a continuously kind of a thing that going, and similarly sulfite oxidase, here the other way around, because sulfite goes to sulfate. So, sulfite has gone having 3 oxygens here, sulfate is having the 4 oxygens. So, therefore, so you have the enzyme in the form of a molybdenum 6 and dioxo, then it binds to the sulfide and the oxygen. Obviously, this oxygen on the thing itself will give a nucleophilic attack at this on the sulfur center and give. So, therefore, you got a sulfate kind of a moiety, and this can come out. In the process, the 6 will go to 4, and this has to, the 4 has to be brought back to 6 by cytochrome C3. 3 means the iron 3 plus. So, it goes to iron 2 plus. So, therefore, takes away electron 1, second time takes away 1 more electron, it will become go back to 6. So, this is exactly reverse to what happens nitrite to nitrate and sulfite to sulfate. Sulfite to sulfate is adding, nitrite to nitrate is removing kind of thing. Okay. So, these are some of the enzymes that we have looked at based on all these biologically important micro or trace ultra trace elements involved in the in this enzymatic chemistry. Now, then we also have looked at, there are some toxic ions. Toxic ions can also be removed. One of the toxic ion, so is the mercury, and the mercury removal, we have looked at the mercury reductase enzymes. So, mercury 2 plus going to mercury 0. So, obviously, the reduced form of the NADPH should go to the NADP plus kind of thing. So, how does it happen? Mercury 2 plus first binds to the cysteine part of this, and then form a kind of a bridge kind of a complex of these 2 cysteinyls, and now this is being reduced by the FAD. FAD. Okay. So, going into this one, FAD going into this one will give the FADH, and this will basically reduce mercury 2 plus to mercury 0, then you will get back your FAD and cysteine sulfurs. So, as you can see that in all these cases, yeah. So, here you have 2 centers here. This one is 136, 141, there is another center. So, the mercury, now let us see that. So, you have here 141 and 136, you have another 556, 559. Now, this is the this is called resting stage enzyme. This will pick up mercury ion from the environment or mercury thiolate kind of a thing, remove this part of it, and that will go into the mercury will go into this particular region first, and then move by the protein conformational changes to this region. So, from this to this will go here, and from here it will basically come out, release out of these by the one more transformation in this conformational changes is going over there. So, from here from NADPH and then gives the NADP plus and the Ag0. Okay. And now, this is again reduced by NADPH, so active form. So, active form, mercury pickup, mercury shifts from one center to the other, and then rearranges into this, and then finally, because there is a bit of redox happening between the NAD FAD to NAD versus this. So FADH minus this NADPH becomes NADP plus, then this is ready to reduce this one, and then the reduction takes place in this too. Okay, the last part of the highlights is on the selenium, and selenium is present in the body only as selenocysteine and no other form, no direct enzyme, but this itself is involved in some of the enzymes. Selenium is one of the important micronutrient deficiency and toxicity. You can see the kind of a Cashin-Beck kind of a disease. This can create growth retardation, cataract formation, Cashin-Beck disease, muscle inflammations, enhanced skin pallor, many kinds of things. So, if you see that the H2O2 reduction with the selenium based enzymes, as you can see, is one set, this is another set, this is called glutathione reductase, and this is called the thioredoxin reductase and thioredoxin. So, glutathione reductase, glutathione glutathione reductase and glutathione peroxidase cycle GR and GPX. Okay, and here the H2O2 for example, and then GSSG goes to GSH and H2O2 will go to H2O. On the other hand, the thioredoxin R and thioredoxin factors, the H2O2 goes in, thioredoxin reductase will take the NADPH and converts the thioredoxin oxidized to thioredoxin reduced. This reduced one will act on the H2O2 and will go back to the oxidized and give the water. So, basically RSEH plus H2O2 giving the selenol. So, this is like a thiol, and this is the equivalent to the acid, and this will make SSE the oxidized form of GSSER, and this is further reduced by the glutathione. So, glutathione and glutathione peroxidase, GSSG plus RACH. So, therefore, glutathione peroxidase selenium is involved in all this. As you can see that the NADPH going to NADP plus will generate the oxidized glutathione into the reduced glutathione. This will be acted by the glutathione peroxidase, and then this will oxidize to that, and in the process this will get the selenium, the lipid peroxides etc. With the presence of the selenium enzyme, they will go into the hydroxy acids and the oxidation of all this. So, glutathione peroxidase contains. So, selenium is a micronutrient. Role of selenium and selenium cysteine in enzymes, glutathione peroxidase, thioredoxin reductase, and thioredoxin reducing the SS in proteins. So, I have more or less covered almost all the highlights of all the enzymes, the initial parts of the introductory part, and then alkaline earth, everything in this. From next class onwards, I will be taking the tutorials. Thank you very much.